Okay, in this presentation we're going to look at Bernoulli Trials. So this is related to a lot of stuff that's coming up on probability later on. So essentially what we have here is we're dealing with experiments here. So many experiments have only two possible outcomes, or we consider the outcomes in just one of two possible ways, either where some events either happens or it does not happen. So we might call this a success or failure. But let's look at some examples here. Let's say, for argument's sake, we're looking at asking a person, do you use Windows? Is your computer a Windows computer? Yes or no. So that's one possible Bernoulli trial there. In favor or not in favor of some government policy or something like that. That's another Bernoulli trial when you just go up and ask them, are you in favor? They might tell you to mind your own business, but well, let's keep things simple. Okay, the most famous one is heads or tails, okay, of a coin. Okay, so when we flip a coin, heads or tails. Okay. Now, this is just a sort of interesting one. So this is where we might sort of could consider something that's not usually a Bernoulli trial, but just to sort of like consider the outcome as a Bernoulli trial. So, for example, a dice roll, we roll a die, six possible outcomes. But let's just say, for argument's sake, we're not really interested in the number. We want to know, does the die roll a six, yes or no? Okay, so die shows a six, die does not show a six. Now, it could be even and odd numbers there. Was the number even? Was it odd? Okay, so let's look at some more that would sort of be relevant to industry, for example, or practical applications. Component is defective, component is not defective, okay? So that's straightforward enough. Is your item broken? Yes or no? And finally, item on individual on time for work or individual not on time for work. Okay, so I get another one there that actually might be just as useful is sick or not sick. Okay, so let's move on here. So clearly these variables are categorical, but we can code them using a binary random variable x. Okay. Okay. So essentially, x is 1 if the event has occurred, and x equals 0 if the event has not occurred. Okay. Now sometimes actually, I'm just going to sort of add this little bit in here. So we might actually call the event we're interested in a success, and if it happens, we call that a success, and if it did not happen, we call it a failure. Bit of a slightly odd way of looking at it, considering what we consider a success later on. But that is just to sort of like match up all the various components of all and terminology that we're going to use. Okay, so probability of success, probability of x equal to 1 is probability that the event occurs, and probability of x equal to 0, which is the complement event, and 1 minus the probability of a success of an occurrence. Okay, so that's the probability that the event does not occur. So that's the probability of a failure. And again, these are complements of each other. So that's just simply the complement rule. Okay. So for simplicity, we let P denote the probability of a event occurring, okay, and 1 minus P the probability of the event not occurring. Okay, so we're usually interested in P, the event occurring. We're usually interested in the success, okay, and we denote that P, okay. So 1 minus P, rather than have separate notation, we just sort of denote the probability of a failure. 1 minus P. So this is the probability distribution, very simple setup here. X, the two possible outcomes, okay. 1 and 0, we're slightly more interested. I know that it's not intuitive to actually put it in that sort of order, but we're more interested, usually more interested in the 1, the success. So anyway, that's how we might sort of write out the probability distribution, and this is known as the Bernoulli distribution. Okay, now, so note that the probability distribution can be written as the probability of x equals small x is px times 1 minus p times to the power, sorry, p to the x times 1 minus p to the power of 1 minus x. Okay, and you can sort of check that there, just plug in some numbers there. Okay, now sort of bit of a strange thing to sort of, why am I coming out with this all of a sudden? Just bear with me, just hold on to that for a while. Okay, so that's a very nice little formula there. Okay, so now the Bernoulli distribution is we're going to look at the random variables. Okay, so it is the expected value. Let's just remind ourselves that the expected value is simply the xi, where xi is all the possible outcomes of the distribution times the probability of those outcomes. Okay, so in the first case we have 1 times p and 0 times 1 minus p. Okay, and that is p. And we also can sort of square that to find e to the x squared. X squared is, in this case, is 1 squared, and just multiply that by p, and also 0 squared 1 minus p. Again, it's p. That's nothing really interesting there. Nothing amazing here. If you remember this, the expected value of discrete random variable, that's all we're really doing there. Now, the variance is more interesting. Okay, so these are the two components to sort of calculate the variance. Okay, and you're going to sort of see this a lot. This particular component here. Okay, that's going to pop up a lot. Okay, but essentially what we're going to do there is just use all of the pieces of information we gathered, for example here and here, to sort of and put them into this formula to compute the variance of a discrete random variable. Okay, and there we have it there. It is p times 1 minus p. Okay, that's very important. Okay, the standard deviation is simply the square root of that. So essentially I'll just sort of zero in on this part here. That is actually really important for later on. So just sort of remember that, and remember where it came from as well, because that's sort of good to know. Now, formally writing it out, the Bernoulli notation can be summarized via the following key formula. So that's a sort of a little bit of a summary there. Okay, so essentially just how to sort of write it out, formally state the distribution in a mathematical sense. Okay, that's not really absolute value, it's just sort of putting it in brackets there. Or to try to highlight it. Okay, but those are the key components there. Okay, now again, really, a lot of it's sort of good to know what how the Bernoulli distribution works, and it's sort of good to be sort of keep an eye on all of these sort of relevant components here, particularly that the domain is simply just 0 or 1. Okay, but yeah, we'll remind ourselves of these values later on, because we're getting up to something more important. So I'll tell you what, I'll just do this little sort of example here. Defective component. Consider the experiment of inspecting resistors produced in a factory. Let's assume that the true proportion of defective units is 1%. Okay, so the probability is 0.01. Selecting resistor randomly from the line for inspection leads to a Bernouilli trial. Okay, with a probability of x equal to 1 equals 0.01, and probability of x equal to 0, 0.99. And remember, that is 1 minus 0.01. Okay, equals 0.99. There we go, and we can write out the probability like that. Okay, so, and that is the expected value down there. Okay, now what I'm going to do here is, I'm going to come back to this, but just later on. This is a very major topic here. It's called hypothesis testing. Now, but I'm going to sort of, once you get to that section, you'll sort of say, oh yeah, great that we did all that Bernoulli distribution stuff. Okay, so rarely do we know the true proportion of P. Okay, let's just go back here and look at my production line. Okay, so let's assume that the true proportion of defective, so we're assuming it, we're just making a rough guess that the true proportion of defective units is 1%, but we don't really know. Just remember that. Okay, so rarely do we know the true proportion P. Okay, however, we may hypothesize something about its true values. For example, we may assume that P equals 0.4. So that might be related to something else, like proportion of the population carrying a genetic disease or something like that. Okay, we can estimate P using a sample, which we're going to discuss later on. Okay, or that, as we've discussed sampling later on, which gives us an estimate here. Okay, so this is a estimate for the true proportion. Okay, and we're going to see that p hat. I'm going to call that p hat. Okay. So if p hat is close to 0.4, we can conclude that the true value of p is as we hypothesized. Okay. So using the Bernoulli distribution theory, which we've just seen there, and the central neighboring theorem, which is stuff we have to do later on, we can test this formally. Okay, so we're building up to something big here. Okay, so that's just a quick sort of intro to the Bernoulli distribution, and we'll sort of pick this up now in the next video.